Neural networks are configurable circuitries that can approximate functions, and they can infer their configurations from examples of inputs and outputs using backpropagation. In the previous videos of the Neural Networks from Scratch video series, we took a look at the backpropagation algorithm and applied it to our XOR example with a simple neural network that consisted of 2 layers. Specifically, we calculated all of the derivatives of the loss function with respect to the individual inputs, that is, the weights and biases of the neural network, the things that we can configure. And we did so by hand using the chain rule. Today, we want to take a look at the problem calculating the individual derivatives with respect to all of the inputs from a slightly different perspective using computational graphs. In the end, we will be able to use this representation to derive all of the individual configurable parameters of the neural network. So let's start to represent a very simple expression in a computational graph to see how it works. And this example is highly inspired by the example used in the book Learning from Data from Gilbert Strang, which I would highly recommend you to read. I put a link down in the description. The basic idea of a computational graph boils down to breaking up all of the atomic operation inside an expression such that you have the inputs at the very beginning and the outputs at the very end, where all of the middle part is the little operations that take place to come up with the output. So let's start with writing down the expression we try to represent in a computational graph. That is a function f that takes in 2 inputs, x and y, and it produces an output by squaring x, multiplying that by the sum of x and y. So as any other graph, a computational graph also consists of nodes and vertices, where a node represents an input or an atomic operation, for example, adding or multiplying, and all of the connections represent how these nodes are connected, how the inputs flow through the operations and produce outputs. So we said a computational graph consists of nodes, of inputs, and in this case we have 2 inputs, that is x and y, and we can come up with nodes that are called x and y. And now we need to express all of the individual operations inside that function as nodes, intermediate nodes. So let's try to break down this calculation. We have one part that squares the x, squares the input, and we have one part that adds x and y together, and then we have one node in the end that multiplies both of these intermediate results together. So let's write that down. Let's say we have one node that is responsible for adding 2 inputs together, and we call the result of this b. We make it a node, and now we want to represent the connections, the inputs that flow through this node. That is, in this case, x and y. Both of these inputs are required for b to make an operation, to produce a result. And then we have the second node, which is just squaring the input, and let's call that a. And obviously a takes x as an input. And now those 2 intermediate nodes are used as an input for the final node that we call f, and this node takes a and b and multiplies them together. So this graph now represents the function and all of its intermediate atomic operations and represents how all of the inputs flow together and connect. So a computational graph is basically a very visual explanation of how the calculations inside that function work. But why do we use this? The entire purpose of this is now to use this to calculate all of the individual derivatives of the output with respect to all of the inputs. And we do so by traversing the computational graph from back to front, as we did in backpropagation as well. And we do so by using the chain rule. So at each node we have to calculate the derivative of the parent node with respect to the child node. So we said we have to traverse the computational graph backwards to get all of the individual derivatives with respect to the input. Thus, we have to start with the output, that is f is equal to a times b. So what we now have to do is start with this node at the very end and calculate its derivative, its local derivative. That is the derivative of the output, that is f, with respect to the current node, that is also f. So in this case it's very trivial, this is just 1. And we make this also a node for the backwards traversal of the graph. Now we have to look at the child nodes, at the inputs of this node, and calculate their individual local derivatives. So we have two inputs for this last output node, that is a and b, and we now have to come up with df, the derivative of the parent node, that is this, with respect to the current node, that is in this case a, and we need it for the other input, that is the derivative of the parent node, that is f, with respect to b. Now when we look at the formula, f is equal to a times b, then derivative of f with respect to a is b, and the derivative of f with respect to b is a. Okay, so we have these two nodes. So now we have to look at the child nodes, at the inputs of these nodes. That is x and y in this case. And let's start with this case, with the a node. The a node has the input of x. That means we have to calculate the derivative of the parent node, that is now a, with respect to x. And the derivative of a with respect to x is the derivative of x squared with respect to x, that is 2x. And we also have to do this for the b node and look at its input. And the b node has the inputs y and x. So we create two new nodes. That is the derivative of b with respect to y, which is equal to just 1, because b is equal to x plus y, and the derivative of b with respect to x. That is also equal to 1. So we start at the very back and work our way to the front, calculating at each node the individual derivative, the local derivative, with respect to the parent node. We basically traverse this computational graph backwards. And what we see when we traverse this graph backwards, that we end up 2 times at the input x and 1 time at the input y. So 2 individual paths end up at the same input. That means the input contributes to the change of the output in 2 individual ways. So in the end, we wanted to calculate the derivative of f with respect to all of its inputs, that is the derivative of x with respect the derivative of f with respect to x, and the derivative of f with respect to y. As we can see, this backwards traversal ends only in one place up at y. And now we want to come up with df dy. Well, how do we do this? Well, we know from the chain rule that we can now just multiply all of these individual local derivatives together, multiply them together, and we get the derivative of the input with respect to the output. So we take df, that's the very node at the back, then take the next node in the backwards traversal, that is df, db, and the next node, which is db, dy. That is exactly what the chain rule looks like. So for x, it's a little bit more tricky. We said that x contributes in 2 different separate pathways to the output and contributes to the change in 2 different ways. That means we have 2 paths that end up at x. And what we now have to do is add those paths together. That means df dx is equal to the first path, which is df times df dA. So that's the path up here, times dA dx. And now we have a second path, which we said we have to add to the first one. That is df times df dB times dB dx. And if we now plug in all of the values for this example, we get df dx is equal to 1, df is 1, df dA we said is b, and dA dx we had in this node, this is equal to 2x. So times 2x, and then plus df df is 1, df db is a, and db dx is 1. So that means this is equal to 2xb plus a. So if we look at this, this makes a lot of sense when we recall the product rule. So we have a product of two functions, f is equal to a times b, and the product rule says that df dx is now equal to the derivative of a with respect to x times b plus a times the derivative of b with respect to x. So that is the first part derived times the second part, and plus the first part times the second part derived, and dA dx is equal to 2x times b plus a times dB dx is just 1. And you see, this is the same thing. So by traversing through the computational graph in a backwards manner and adding up the paths that contribute, the paths that end up at the same input, we get the same as the product rule. And for our df dy, we get 1 times a times 1, and so that is equal to a. So this way, we have a very visual representation of how we can use the chain rule and all of the individual derivatives, the local derivatives at each node, at each operation, to get the derivative of the output with respect to the inputs. And what we could now do is take a neural network, break down the neural network to all of its individual atomic operations, and derive all of the changes in the input by using this computational graph. A big advantage of this graph is that it's very visual and quite intuitive to get into. And what all of these frameworks are doing, like PyTorch and TensorFlow, they are trying to come up with a graph such that they can traverse this graph backward and calculate all of the derivatives automatically. So that's called autograd or automatic gradient. So in this video, we saw that we can use a computational graph and the backward traversal in particular to come up with all of the individual derivatives that we need to propagate the error of the output back to the inputs. So we construct the computational graph and then we do a backwards traverse with the individual local derivatives of the nodes, and if multiple input nodes are used more than once, we have to add the paths together, and then eventually we can come up with the final derivatives of the output with respect to the input. So today we looked at computational graphs and how we can use them to get the individual derivatives of the output with respect to the inputs. That's very useful for neural networks and is especially a very intuitive approach and a visual approach to the chain rule. In the next video, we will start with a very basic implementation of a XOR network in Python. And we will do so using no automatic derivation. We will do it all by hand and lay it out all from scratch, just using PyTorch tensors. So stay tuned, leave a like and subscribe if you want. Bye.